Hello everyone, I'm Lara Moreno from Eprosima, and today I will host this embedded working group. As a recap, on our last working group, we had here Farah Naderi, co-founder and chief tech officer at Careta Robotics, and he presented two projects about artificial intelligence. The first combined PX4 autopilot, ROS2, PX Hub 6X, and micro-RCD DDS for precise drone position. And the second project was about PitchHawk, Raspberry Pi CM4, ROS2, and micro-XRCE DDS to enable drones to track and follow objects in real time. If you miss them, you can access the videos and watch them on our YouTube channel. And today we have here Dr. Ilia Ovsiannikov, co-founder of REMAKE.AI, and he will discuss the integration of micro-ROS into open source home pet companion robots developed at REMAKE.AI. In the talk, we cover the architecture of these robots, the utilization of micro-ROS, and the wide range of benefits it offers to consumer robotic products, including improvements in architecture and economics. Dr. Ovsiannikov will share insight gained from the project, suggesting that micro-ROS could potentially see widespread option in consumer applications in the future. So please, Ilia, if you want to start, you can share the screen. And so
yes.
perfect. Thank you very much.
Okay. Well, hello everyone, and thank you for inviting me to speak at this meeting. My name is Ilia Ovsiannikov. I'm a co-founder of REMAKE.AI, and what we do is we focus on home robots. In this case, I will talk about pet robot. So let's take a look at that. And we're located in Los Angeles, California, so that you can have some better understanding. Before I start, I'd like to say thank you to the micro-ROS team, including Pablo. As far as I understand, Pablo, you're the boss of micro-ROS. So, and I'd like to say thank you to the many ROS2 developers, because we're using micro-ROS very much, and it's a great software, and it's very helpful to us. So let's go on, and please stop me if I move too fast or you have questions. Please don't hesitate to ask the question. So here's a look at the robot. Right now, the product is it's a kit. It's a kit for a DIY kit for STEM students and for makers. It's a 100% ROS2 robot, and it's 100% open source. It in some ways it resembles Turtlebot 3 Burger. It has a LiDAR. It has a two-wheel differential drive. It performs ROS2 mapping and navigation and SLAM, and it's designed to be very simple and exceptionally affordable compared, say, to the Turtlebot 3. So it runs to to make it affordable, we had to change a few things. It runs on Arduino ESP32 microcontroller, not on Raspberry Pi, and it has a 3D printed body. So because it runs on a microcontroller, not on Raspberry Pi, it allows to make it much cheaper, much more affordable. For more information, there are these websites. Makerspec.com is the website that focuses on the hardware, on the DIY hardware of this robot. And there is KI.AI website. It focuses on the software part of this project. And there is remake.ai. It's the business, it's the startup website. So we've designed three models of three sizes for this robot. Here I have a 200mm model and a 300mm model. The 200mm model fits some popular 3D printers like Prusa, MK3, and like similar sizes, printers of similar sizes. So this printer can be the smaller robot can be 3D printed fairly easily. The bigger one requires bigger 3D printers. So this is for advanced makers, so to speak. All right, moving on. This is how the kit looks like. Most of the parts are the 3D printed like body components. And there is on the top there is the breakout board for the ESP32 microcontroller. It's very small. And going next to the right, there's because so let me explain a little. Because we've removed the Raspberry Pi, and Raspberry Pi is quite power hungry on its by itself, so we can save quite a bit of power consumption, and this robot can actually run on alkaline batteries, which brings down the cost. Of course, it can run also on LiPo batteries, but for like sort of for starters, it can very well run on alkaline batteries. Next, it uses a couple of brushless motors, and there are a couple of 65mm wheels. And there is the LiDAR, the low-cost LiDAR, and there is a caster wheel, and again, there are 3D printed body parts. All right, so moving on. So this is what the robot can do. This is pretty standard. It performs the mapping, it performs the navigation and SLAM, nav2, and cartographer. And let me see if I can run a few seconds of the instructions video. Oh, I think it's possible. Sorry, it looks like maybe it wasn't shared. Just 1 second. Entire screen now. Cannot. Yeah, there you go. I'm sorry. One more try. One more try. All right. So this was the beginning of instructions video, and I hope you can get some understanding what this project is about. So this robot is supposed to be fully autonomous, and it's supposed to just run around and play play with the ball, play boxes, play with different things, and entertain the owner and keep company. So behave like a pet, demand attention, and do things like this. So this project is still in progress. So what's done is the ROS robot. There is quite a bit of work after that comes after that. That is still in progress. So the next slide is, let me see. So here I have some links for reference. We don't have to take a look at them now. This is just for reference for offline viewing. Okay, the next slide shows the architecture. So on the left we have the robot. It's based on Arduino. It's using the ESP32 microcontroller, and the core of it is micro-ROS. Micro-ROS connects it to a local ROS2 PC over Wi-Fi. Something else the robot does is it has two libraries. One is the LiDAR or LDS, laser data sensor, distance sensor library. That library captures data from the laser sensor, and it also controls the laser sensor, the scanner, and it forwards that data over micro-ROS, over the Wi-Fi LAN to the ROS2 PC. So also there is a motor control library. It controls the differential drive. So there is also a Wi-Fi access point here, and I will talk about this a little later. This is a built-in web server. It allows configuring the robot easily using just a web browser, so to make it connect to the Wi-Fi and to set up its properties, the robot's properties. So let's see what's running over micro-ROS. The most important thing that's running is the telemetry. It's the telemetry topic. It's a best effort transport. And what it's sending a message that encapsulates raw LDS data and abbreviated odometer and joints data. And we will take a look at this a little more in a next slide, one of the next slides. There is also ROS out for logging. What comes back from the ROS PC is the CMD vel command, the velocity for the motors. This command gets parsed and processed by the robot, in the Arduino firmware, and it controls the motors. Also, the robot's firmware implements ROS2 properties server with properties that the ROS2 PC can access. So on the PC side, it runs in a Docker container. It runs on Windows and Linux. Of course, there is micro-ROS, and what's happening, the key point here is that the telemetry topic, it it goes into the telemetry package, and that telemetry ROS2 package, it converts the raw data into proper ROS2 topics: the scan, the DOM, and joint states. So that's that. And of course, the PC runs the navigation, the mapping, and everything else. One more look at the hardware. So this is the ESP32 microcontroller, and it comes with this tiny board. It plugs into this tiny board with a switch and with some connectors on the back. Next to the connectors is a DC regulator. It converts 24 volts from the battery into 5 volts for the laser scanner and the ESP32 itself. So the connectors are like this. 2 of them are for the motors. 2 of them for expansion. I will mention about this a little more later. There is one, of course, power connector, 24 volt, and there is one connector for the laser distance sensor. There is also a connector, it's optional, for the front sonar. So that's that. Again, there is no Raspberry Pi. This becomes much simpler and smaller and less expensive when we switch to using a microcontroller. So this slide is about so there's a bit of a problem when we switch to the microcontroller. There's a bit of a problem because laser distance sensors, low end laser distance sensors, they come with manufacturer SDKs, including ROS2 sample code, and those SDKs, they usually require having a serial port to plug the laser distance sensor in. And we don't. The MCU, of course, has a serial port, but the SDKs want the serial port to be on the ROS machine, which can be a PC or Raspberry Pi. So we have to somehow forward the data from the forward the laser distance data from the robot, from the MCU, to the ROS machine, to the ROS PC. So the amount of data that the laser distance sensor generates, a low-end LDS, is between 6 kilobytes roughly and 16 kilobytes. The amount of data depends on the LDS sampling frequency. So on the lowest end, we have LDS sensors with 1.8 kilohertz frequency. That is 1.8 thousand samples per second. So each sample is usually occupies 3 bytes, and there is some overhead. So if you multiply out the numbers, you get the 6 kilobytes per second. On the higher end, in this category, we have LDS that run at 5 kilohertz. So those generate about 16 kilobytes per second. All right. So next slide. So as an so we would like to make this robot and its kit as affordable as possible. And one of the obstacles on this way is the cost of the laser distance sensor. So, one way we're taking care of this problem is we've connected this robot to a large number of low-end laser distance sensors, and thankfully, because of the proliferation of vacuum cleaner robots, nowadays there are many laser distance sensors from those vacuum robots available, and they are quite inexpensive. So we support lots of those sensors, and this helps bring down the cost of parts. Okay, so I'd like to mention something before we move on from the slide, is that because those laser distance sensors, some of them or many of them are optimized for vacuum cleaner robot use, they lack motor control, built-in motor control. The motor control, the PID loop, the PWM, control, it has to be external. So it has to run in Arduino in this case. Anyway, so moving on, this is just a list of considerations. We don't have to go through this. It's for offline reading if you're interested. Basically, it says the only so we want to forward LDS data to the ROS PC, and UDP is the best way to do this because it's fast. We don't care about some data loss usually while streaming data, and other solutions, they don't quite fit as well this use case. So micro-ROS, that's streaming data over UDP, is the best in this case. Let's see, and this is the current solution. So what's happening is this: we had to split the laser distance sensor control operation basically in two parts. Part of it is running on the robot, and part of it is running on the PC, on the ROS2 PC. So what's running on the robot is the control of the motor. It has to be local in this case, pretty much. Also, and there is a library, LDS library, that takes care of this in the Arduino firmware. The second thing is that the library sends the commands and checks the responses from the LDS. Next, the LDS library captures the LDS raw data and forwards it over micro-ROS to the ROS computer, to the ROS2 PC. This LDS data library also can decode the data into the point cloud right on the microcontroller, and this can be useful for low latency obstacle avoidance. But this is optional because this requires extra calculations. So once the raw data from the LDS gets over to the ROS2 PC, it gets decoded one more time, if you will, and converted to the scan topic messages. So basically, the flow of data is one way when it comes to the ROS2 PC. So this is not an ideal solution, and because this, so what happens is that when because we cannot plug the LDS sensor into the ROS2 computer, we cannot reuse those SDKs, those wonderful SDKs and the ROS2 sample code provided by manufacturers. So it's and to as a workaround for this, we have to basically port some of that code from those SDKs, the code that decodes the stream from the LDS, and extracts the raw data and extracts the speed reported by the LDS. So we have to extract and port that code into the Arduino library and the ROS2 package. But this is doable. It's extra work. But it's doable. And I have to say that this architecture works very well thanks to micro-ROS. It seems to work very well in our tests over Wi-Fi. All right, so next, so this is the telemetry package. This it lives on the ROS2 PC. So as I was mentioning, it receives the raw data and it converts the raw data, the abbreviated odometry, joint positions, velocity, and the raw LTS data. It converts to the scan topic messages and to the odometry topic messages and the joint states topic messages. And this is the message, the custom message that we're using. So the odometry is abbreviated. The full odometry message can be quite big, so for a microcontroller to handle. Next, okay, so this is just a quick slide about the ESP32 firmware. So this is Arduino, and it's using the micro-ROS for Arduino library. The other libraries it's using, it depends on, is the LDS library that we wrote. It depends on the motor control library that we wrote, and the motor controller, the motor control library uses PWM and PID control, and basically it receives the pulses from the encoder and it keeps track of those pulses. And it's using the web server for configuration. Let's see. Okay, well, this is for offline reading if you're interested. Otherwise, I will just move on to the next slide. And just a quick note that we had to experiment and with the choice of the size of the message for the micro-ROS. To carry, for the telemetry message, and messages too long, they become the transmission becomes unreliable. We get lost messages. Messages that are too short, they apparently incur too much overhead. So currently, the sweet spot seems to be around 400 bytes of data. That works very well. Okay, next slide. This is the micro-ROS for Arduino. So we've made a fork, and thank you very much again for the micro-ROS software. And for it being open source. So we've made the fork and we've configured it for this robot, for this particular project. We've added our message type, and we made it to work on Windows, build on Windows, because this this project is trying to attract Arduino developers, students, makers, and there are lots of them. Arduino is very popular, and they often use Windows as their platform. So we've added extra five services for the parameter server in the Colcon.meta. So we've tweaked a little bit of the code, and we've taken out the Wi-Fi begin out of this set micro-ROS Wi-Fi transport function, because we want to take care of the Wi-Fi connection ourselves. And there's some miscellaneous tweaks. So we've also packaged the this configured library, and we've published it on the Arduino in the Arduino library manager. So it's it can be downloaded through the Arduino IDE. Okay, so next up, so this is a few slides about the configuration of the robot. So unlike the Turtlebot 3 with Raspberry Pi, the configuration of this robot with the microcontroller, this is done through this tiny web server that's sitting in that microcontroller in the ESP32. So whenever the robot is unable to connect to Wi-Fi for whatever reason, it enters the configuration mode. And in the configuration mode, it launches this little web server. And then I can connect to that Wi-Fi, to the robot, to the robot's Wi-Fi, and then open a page, navigate to this IP address, and then I get the configuration page. Here I can set up the Wi-Fi access, select the enter the Wi-Fi network name, SSID, its password, then also enter the IP and the port for the micro-ROS connection, and then I can configure some robot properties. The first one is basically it's the model, but basically it's the size of the robot. It's 200 millimeters, 250, or 300. The second one is which laser sensor are we using? There are many of them supported. And the next one is the motor model. There is a selection. They have different RPM, basically. So just a quick slide. On the left, this is the list of the models supported. So the three models that we provide, and there is and you can also have a custom one with a custom size. And on the right, there is the list of sensors, laser distance sensors supported, and this list keeps growing. Let's see. Next slide is the list of motors. We don't have to pay much attention to that, but basically, all we need to know is the RPM, maximum RPM, and how many pulses per revolution of the encoder the encoder of the motor generates. On the right, okay, yeah, that's what the slide on the right says. Okay, and this is the size of the robot, how we configure the size. Essentially, it's the main thing here is the base diameter. In this case, it's 202 millimeters. And what's the wheelbase, and what is the wheel diameter? And maximum acceleration, it should be specified so that there will be no wheel slippage. It's like a number chosen properly. Okay, so next slide. Okay, so this one slide on the economics. So this is very this is important to us. This is important to us because we would like to make again this kit as affordable as possible for everyone. So the classic, the Turtlebot 3 burger on the left is on the left, and our model is on the right. And I'd like I'm making a quick comparison here. So we got rid of the Raspberry Pi 4 and replaced it with a very inexpensive ESP32 microcontroller. That lowers the cost, of course. Next, and this is thanks to micro-ROS, because micro-ROS is key in this ability to go from from Raspberry Pi to microcontroller. Next, there is this OpenCR board in Turtlebot 3. It is quite expensive, and it's replaced by a tiny breakout board with hardly any components. The expensive servo actuators are replaced with much cheaper BLDC motors off the shelf from AliExpress or Amazon or eBay. The wheels stay same. The LiPo battery is it's optional. So it's good to have, but the robot will run on alkaline batteries. So this brings down the cost further. And this is thanks to the MCU being so much low power compared to the Raspberry Pi. Battery charger, basically none or optional if you still want to use LiPo batteries. The LDS remains, the laser distance sensor, but now we have choices of very inexpensive laser distance sensors, thanks to those come usually from the vacuum cleaner robots. Color camera. So we will talk about this in a bit. So there is no cost for the color camera because we're using a smartphone, bring your own smartphone device. So, and the cost of parts, the Robotics offers it for $600 something, and the total of the parts actually is here I put it at 100, but it's actually it can be made under $60 if just the cost of parts. So what I'm trying to say here is that micro-ROS, thanks to micro-ROS, a certain type of robots like this one, it becomes dramatically less expensive, this so maybe I should phrase it like this. So it helps us clear the hurdle with the consumer acceptance of those robots. When the robots become so inexpensive, their acceptance increases. So also, I just wanted to mention that replacing Raspberry Pi with an MCU seems to simplify the system also. So it's not just about the cost. So because there is no RPI, Raspberry Pi setup, no SSH, no VNC or display or keyboard or things like this, no imaging of the. There are many things that are skipped when we switch to the MCU. All right. So going next. So here's some more fun things. It's like getting back to the pet nature of this robot. So there are extensions to this robot. So I was talking about the base that takes care of the main functionality. So the ESP32 has a couple of connectors that allow. So basically you can connect an extension board that's based on Raspberry Pi Pico. And one of the Pico boards goes into the body, and the other one goes into the head. And those connect to the servers, fan, touch, and various sensors. And same for the body. The body focuses, of course, on the cliff and bumper sensors that are, located in the body. But those are optional. Everything is optional here. So here in the picture we have the head. The robot's head has some ears that can move. There are servers in the head, inside the head, and there is also the fan, a fan behind the smartphone to keep the smartphone cool in case the smartphone is running something power hungry, some processing or like streaming, camera streaming. Okay, next slide. This is how, basically it shows the way one way to add sense of touch to the robot, so that now you can pet the robot once you add it. So this is done. This is an old trick, but it's a good one. You can take a piece of copper tape, sticky copper tape, stick it on the back of the robot's head, solder it, just one wire. It goes to the Raspberry Pi, in this case, Pico, and then the Raspberry Pi Pico can monitor the capacitance of that piece of tape. When you place your hand on top of the robot's head, the capacitance changes. This is the parasitic capacitance with respect to the ground. And the Raspberry Pi Pico ADC can measure that and measure the change. So basically it's charging, it keeps charging the ADC, I'm sorry, the Raspberry Pi Pico keeps charging and discharging the copper piece of tape, and it's measuring the time it takes to charge or discharge. And this is how you can implement the sense of touch. So there is a YouTube video about this, and there is GitHub open source code for this, but I'll leave this for offline in case you're interested. Okay, so next up is smartphone. So this is a bring your own device. Can be a smartphone, can be an 8-inch tablet. It can be an old device. It doesn't have to be something new. And what it does, it acts as a display. It acts as the color camera. It brings the sound. It has the microphone and the speakers, and it also the IMU. So everything gets connected to the cross to PC, and this is not implemented yet, so we haven't got to this yet. But this is, this is scheduled for implementation. So the display interface runs in a browser. So what you see, basically, it will be just a browser running on the smartphone, and it will connect to through WebSockets to the ROS bridge. So we also experimented running ROS2 on the smartphone without root on an Android smartphone. And we got some results. We were able to compile ROS2 on Android. There is some problem, but solvable. But anyway, in the future, it's possible to maybe we will move. Maybe we will have the ROS2 run on the smartphone, and the PC will not be required. The ROS2 PC will not be required. So anyway, so the display is primarily for the facial expressions, so those are fun, and this, especially for, it seems to be appropriate for a pet robot. There's lots of expressions, and this is a JavaScript library. So this is something that gets us started. All right, so next slide, development environment. Basically, this is Docker that runs ROS2. It's a Docker image that contains ROS2 desktop with micro-ROS base and micro-ROS agent on top of that. And I have links to the Docker file and the images for offline browsing. And the PC setup for those who use Windows, we need the Docker installed. We need the Xlaunch, Xserver, Xclient for Windows, and we need the Arduino IDE. All right, next up, so we have basically we've divided the robot as far as social media goes and as far as websites go. We've divided the robot project into hardware, DIY hardware, and software. So those are separate. So this, the Micro-AI website is for the software part. And right now it takes care of the ROS. It has the ROS packages and it takes care of the Arduino firmware, but its role is supposed to grow a lot in the future. So this is very much, this part of the project is very much in progress. So this is supposed to become a software platform for multi-skilled home robots. Multi-skilled is basically you can write an app. So it's like one person can write an app for the robot to play ball. Another person developer will write an app to play hide and seek, and yet another one will write something else. So this is the kind of functionality that we want to enable. And its goal is the wide consumer acceptance of those multi-skilled home robots. So those robots, they will be able to do many things. And hopefully this will be appealing to the customer, so that those robots, based on this platform, will make its way into everyone's home. And hopefully micro-ROS as well, because we use micro-ROS in our case. So there is a teaser video about this concept, about this software platform. So I'll leave it for offline viewing. And just want to mention that, okay, so the Micro-AI software platform, it sits on top of ROS. ROS provides the navigation capability, and it sits on top of the machine learning and AI libraries and processing pipelines that process images and video stream and audio and things like this, with all kinds of recognition, image recognition, object recognition, activity recognition, things like face recognition, and so on. So the first pre-release hopefully will be this year, close to the end, and we are staying pretty much in stealth until then. So beyond, there is only the teaser video available. It still gives a good idea, but we haven't released details, yet. All right, so just want to say thank you for listening to the talk, and for joining. And here we have a YouTube channel. If you want to follow up later, if you're interested, hopefully, with instruction videos and development updates, and a lot of social media links, GitHub, blog, Facebook, pre-launch mailing list, Twitter, Instagram, Reddit, and so on. And that's it, I suppose. We can switch.
Thank you very much, yeah, for the talk. Very, very interesting. Does someone have any question? Any comment? I think that everything was very, very good explained. Sergio, okay, go on. Sergio? I don't know if Sergio wants to make a question or not. Okay, so turn on the video. Okay, sorry. Maybe he's writing the question.
Can you hear me now?
Yes, yes.
Okay. Okay. Thank you for the nice presentation. I was particular. I mean, everything was really, really nice, but I was particularly curious about your approach to the LiDAR sensor. I was working on a similar project, and I also had the same problem, and also the same doubt about how do we deal with the massive quantity of data that the LiDAR sensor sends, right? And also the processing, because it's not only that you receive a lot of that, and in this very constrained microcontrollers, so you need to save all the data, process it, convert it to float, right, with the whatever protocol it uses, whatever encryption it uses for the cloud points. Yeah, and I didn't manage to get like a good solution with a constrained microcontroller. I ended up just doing it in a big processor like you always do. So I'm wondering if you have if this project is open source, if we can find also the library you did for the LDS.
Oh yes, absolutely. Both everything is open source. Both including the Arduino library, with all those LDS supported, and including the telemetry package, ROS2 telemetry package with all those sensors supported. Yes, so everything is open source. And actually, you can just download say the Docker image, and the library will be there. The telemetry already will be set up. So yeah.
Okay, nice. Thank you.
Okay. Any questions? John. Okay, go on.
Yeah, a quick one. So thank you for great presentation. So two things. You mentioned testing a whole load of LiDARs and your experience of using the various ones. If there is anything like that that's shareable, I, for one, would be really interesting, because just trying to work out which LiDAR to pick on the market is actually quite hard, because there is a lot of choice. And secondly, I wonder, what was the biggest challenge with working with micro-ROS for this project?
Well, it's let's see. It was actually a great experience. I didn't. Well, there were there was sample code, and I got up and running very quickly. The biggest challenge was there's still a bug or two remaining that I had to chase down. The main the main problem was that the micro-ROS, when the data is only flowing to the PC, after I think 180 seconds or something like this, the micro-ROS agent stops reacting. So that took me a while to work around. So right now I have to ping the Microsoft agent every, say, 60 seconds as a workaround. So that was probably the only challenge, but otherwise I got running pretty fast, and it was easy. Yeah. And about the LDS, so I do intend to have them tested. But it will take time. Right now, we've connected a lot, and there's a couple more coming. But yes, we will test them and publish the results. This is my biggest question right now too. What is the performance of those LiDARs and LDS? I would like to have the best.
Okay, Sergio, again.
Yeah. I just a comment that I had a similar problem using micro-ROS on ESP. About after 2 minutes, it just stopped working, everything. And in my case, it was how I had the firmware. So I had combined, and it was a problem with memory, with the memory management of the ESP using Arduino for ESP. My workaround was, so in case you also have the same, my workaround was I had a mix of C++ files and Eno files, and I just turned everything into Eno files, and that fixed the problem.
Oh, okay.
Yeah.
Thank you.
That was my solution. Just, yeah, thanks.
Very interesting. Thanks, Sergio.
Okay. Any question more? Okay, so we can close the meeting. I want to thank to everyone to attend the meeting, and especially to Ilia Ovsiannikov for the talk. Very interesting. And that's everything. See you on the next working group. Bye.
Thank you, Laura. Bye, everyone.
Welcome.